So I'm going to be giving really an overview talk about an area that I've become interested in over the last, let's say, 3 years or so, which is on reinforcement learning. So one thing which would be useful at the beginning of this talk is, I can't see your hands, but if you could raise your hands if you have a general idea about reinforcement learning and somebody could do a rough count, that would be very interesting for me. Aha, I can see. Does anybody know anything about reinforcement learning? Okay. There's a couple of hands. Okay, fantastic. So please do stop me at any time. I'm going to be going through some of the mathematical details, but not too much. Hopefully, it'll give you a nice overview of the topic. But please stop me at any time if anything isn't making sense. I can always go deeper into the ideas. Okay. Oh, let's see. Okay. So I actually have a question for you, which you can at least think about, which is, why are you here? Why are you sitting in this room at the moment watching this talk? And this sounds sort of, slightly disconnected from the talk, but in fact, it's highly connected. And the reason for that is because the reason you're here is because you made some choice, presumably, to be here. And you made some choice about being here or being somewhere else. And presumably, I hope, you thought that being here had some value. And that may be value because you simply find it enjoyable to listen to talks about topics that you don't know about. You may have found it valuable because it's something that you want to get into. It may be valuable because you like to be collegial. There are lots of reasons that it could be valuable for you. But the point is that you chose to be here because you believe that being in this state at the moment has higher value than being in other states. And I don't just mean the sort of the local value of being in this state. I mean potentially the sort of long-term value. So it may be that you're here because you want to learn about reinforcement learning, because you want to do more research on it, because you want to, get a position somewhere in this field, which can earn you money, which can put food on the table. And so all of this entire sort of line of consequences is to do with the value that you see in being in a particular state and making a choice. And in some senses, this is how we interact with the world in any situation we're in. It's not always conscious, very often it's entirely unconscious, but we make decisions based on both value in the sense of, the local value and the sort of global value about, what's going to happen in the future based on the particular choice that you make. So one could say that you have a sort of policy where by a policy, we mean a set of choices of actions as to how you move through the world. Okay. And in essence, reinforcement learning is all about that. Reinforcement learning is a type of machine learning which allows what's called an agent, you can think of it as a robot or a computer, to perform some set of actions optimally by finding the states which are most valuable to it. And we're going to define policy and value and states and rewards and all of those sorts of things in a bit. But that's really what you should be keeping in mind. You should be keeping in mind some sort of agent, which is maybe playing a game or performing some task, where there is a well-defined set of what we'll call rewards. And one of the ways that it can do this optimally is to find the states which are most valuable to it and try to move into those, i.e. take actions which will move it into those states. Okay. So the basic plan for this talk, and I may not get through all of it, but we can see. So first, I'm going to talk a little bit about where reinforcement learning fits into artificial intelligence as a whole. I'll give you an overview of what reinforcement learning does and the basic idea. And then we're going to have to go a little bit into the mathematics of it, which I promise won't be too much, talking about Markov decision processes. And then from that, we can really define reinforcement learning a little bit more technically, and then talk about the different methods. How can we actually get an agent to perform a task using the reinforcement learning framework? And some of the ways of doing this are going to be value iterations. We'll talk about Q-learning, deep Q-learning, and maybe we'll get onto some recent developments. So probably the best resource for learning about this is the book by Sutton and Bartow. It's called Reinforcement Learning. It's a truly fantastic book. They actually put it online for free, so you can download the PDF, but I highly recommend getting a copy of it. It's the sort of book that you can sort of put by your bedside table and read. It's extremely readable, but it's got all of the details in there as well. And then the Deep RL Bootcamp, which you'll find on YouTube, and 2-minute papers from time to time has some nice resources on reinforcement learning as well. So first of all, I just want to put things in context to talk about the relationship between AI, machine learning, deep learning, supervised learning, unsupervised learning, and reinforcement learning. So this picture here, we see the entire field of artificial intelligence, where, can you see my mouse, by the way? Is that showing up? A nod from anybody? I'm not seeing it.
Yes, we are.
You can. Okay, fantastic. Great. So we have the entire field of artificial intelligence, and within that is the field of machine learning. And machine learning, I mean, this isn't a sort of perfect Venn diagram, but within machine learning, there are really three different fields. There's supervised learning, unsupervised learning, and reinforcement learning. I'm just going to quickly talk through all of those. And then there is a method by which you can sort of perform these different types of learning, which is using deep neural networks. And this is deep learning. Okay. So within artificial intelligence, there are actually things which are not machine learning, but which are artificial intelligence. And they tend to be rule-based systems whereby an agent, an artificial agent, is able to perform some task by some handwritten set of rules. And so, for instance, you might be able to program a computer to tell the difference between cats and dogs simply by hard coding in what a whisker looks like, what a tail looks like, what cat ears look like versus dog ears. This is not machine learning. This is hard coding in the rules, but it is still a form of artificial intelligence. Now, machine learning is really about learning from data. And within that, there are different ways of doing it. So within supervised learning, you have what's called labeled data. So you have some data set. And for instance, we're looking down here at the bottom left, you might have some data which says what percentage of people are outside when the temperature outside is a certain number of degrees centigrade. Okay, so maybe you find that around 25 degrees is when most people are outside, and then as you go down, there are fewer people, and as you go up, again, there are fewer people. But all you have here are the points, the data points. And what we mean by labeled data here is that we know here, given a particular temperature, we know the percentage of people outside. And the simple act of supervised learning is to take this data and to be able to fit some function through this data so that we can make predictions. So we want to be able to then look at unseen data, and unseen data might be, okay, we don't actually have any data for what happens when it's 30 degrees outside, but using the function, we can make a prediction of the percentage of people outside when it's 30 degrees. Okay. So that's a very simple example of supervised learning, and it's an extremely simple one. We've got a very simple function. However, there is the field of deep learning within supervised learning, whereby it's a similar sort of idea, but rather than just fitting some very simple function, the type of function that we actually fit is in the form of a neural network, and in particular, a deep neural network, which is a type of neural network, generally with a few hidden layers in the middle. And if you don't know about neural networks, that's not a problem. I can either tell you about them another time, or for now, don't worry about it. But an example of deep supervised learning would be the so-called galaxy zoo problem, whereby there's a catalog of galaxies, and those galaxies are labeled into elliptical, spiral bar galaxies. There's an entire sort of classification of that. And using a neural network, using generally something like a convolutional neural network, because the data is labeled, you can train the neural network such that when it sees a new picture of a galaxy, it can classify it appropriately. Okay. Now, within unsupervised learning, we don't have any labels on the data. And what you might be able to do there is something like clustering. So if you look here, we have a set of data, and we can see, it doesn't actually matter too much what these axes are, but we see that there are sort of clusters within this data. And an unsupervised learning algorithm would say, okay, this here is one cluster, and then we have another cluster, for instance, over here. And it could say, it can't tell you what those clusters are. It could simply say, okay, we're going to label this cluster A and this cluster B. Okay, you can then go through yourself and label it and say, okay, now having found the clusters, we know what these sorts of data are, and these sorts of data, and we can then label them ourselves as, you know, whatever the particular categories are. But the point is that within unsupervised learning, we don't have labels. We simply look for clusters. We look for patterns in the data. There's an example here of unsupervised deep learning. These pictures up here is from something called a GANs, a generative adversarial network, or a GAN. And this, I think, is actually taken from something called CelebGAN. And these all sort of look like celebrities, but in fact, these people do not exist. There's actually a rather nice website, I think it's called This Person Does Not Exist. And it uses a particular architecture to generate pictures of people using a deep neural network. But strangely, the neural network which is producing the pictures of people has never actually seen a picture of a person. Again, another time I can go into the details of that. Okay. And then here we have reinforcement learning, which I'm going to be talking about in detail, and then the application of deep neural networks to reinforcement learning. Okay. So I want to ask at this stage, are there any questions about this? I mean, the reinforcement learning is what I'm going to be going into in detail, but if there are any questions about the rest, I'm happy to answer. Looks like nothing at the moment. Okay. So my personal interest in machine learning is sort of the relationship between ideas of machine learning and human cognition and affect, where affect is essentially related to emotion. I'm particularly interested in how we can utilize ideas of human cognition to improve machine learning algorithms, and also using machine learning algorithms to try to understand aspects of human cognition and affect. So that's really my interest, in particular about a framework called active inference, understanding attention, and even sort of delving into consciousness. And then using ideas of human cognition to understand ideas about attention, communication, something called offline learning, and saliency, which is to do with, if you're looking at a picture of a cat, it's very clear to you which parts of the picture of the cat are important. But you can also get a neural network. You can sort of propagate back through the network, and you can actually get the network to tell you which were the regions in an image which were salient to the particular choice of category that it came up with. Okay, so now we're going to talk about reinforcement learning, and I'll sometimes call it RL. And it really comes about from a combination of a couple of disciplines, one of which is from psychology, the idea of learning through trial and error, and also the idea of secondary reinforcers. And the idea of a secondary reinforcer is essentially the idea of Pavlov's dog, where with Pavlov's dog, I mean, the story is not exactly the truth, but more or less, Pavlov rang the bell, and the dog started to associate the bell with food. And the point here is that the dog started to salivate when the bell itself was rung. But of course, the bell itself has no intrinsic value. The bell only has value because it's associated with something else. Okay, and so that relationship between one thing which doesn't have intrinsic value, but which leads to something which does have intrinsic value, is very important within reinforcement learning. And then on the other side, we have the idea of optimal control theory, where we'll see ideas of value functions and dynamic programming, where dynamic programming is really a programming paradigm that was used within optimal control theory and is used. Oh, was there a question there? Oh, so dynamic programming can be used in lots of different areas, but it's been used within optimal control theory to find optimal value functions within some system. We'll talk about that in a moment. But it's not really learning in the same way that we think about it often. But you put these two together, and you get the realm of reinforcement learning. Add on so-called temporal difference methods, which we'll look at later, and this gives us the sort of modern guise of reinforcement learning. So I just want to give some examples of reinforcement learning in action. And what we're seeing here is a game, just one of the simple Atari games, where we have a paddle at the bottom, and the aim is for the agent to move the paddle left and right such that it can knock the ball onto the bricks. And I'm not telling you how it's doing it at the moment, but we can see in the process of training, it starts off very badly, has no idea what to do. All it sees are the pixel values, and the feedback that it has is the score. And after a couple of hours of practice, not knowing anything about physics, not knowing anything about balls and paddles, it's able to get up to a sort of a good human level. And then you give it a little bit more practice, and it actually finds not quite a bug in the system, but it finds a way to solve the problem even better than most humans would be able to. It finds that there's a sort of easy way through. If it creates a little hole up the top left here, which you will do in just a moment. I believe, there we go, it can sort of solve the problem, as it were, much, much faster. Okay, and so this is an example of reinforcement learning being used to train an agent, and essentially it's working through trial and error, and it's finding the states that it needs to be in, which lead to the states where its reward, which is the score, increase. Okay. Go is another example, and if you haven't seen the AlphaGo documentary, I highly recommend it. Go was thought to be a game that was really far beyond the reach of what computers would be able to do in terms of human levels. We sort of cracked chess some time ago with Deep Blue, but it was thought that the game of Go was just way too complex. The state space is far, far too high. Even if it looks like a simpler game, it's actually, in terms of strategy, it's much more complex. But AlphaGo was developed, and it actually turned out that it was able to beat Lee Sedol, who was the reigning world Go champion and had been for some considerable time. And not only was it able to beat him, it was able to beat him in a way where, in a particular move, which if you see the documentary will explain it, it was seen to be a move which was very confusing to everybody watching. The computer played a move which everybody thought that it had gone sort of off the rails, it had gone wrong. But Lee Sedol came back to the table and realized that what it had done was to create a new type of strategy which no human had ever thought of. And for any decent definition of creativity, I think this is computers being creative. And that's something that people often think computers aren't able to do. You know, they can sort of reproduce what a human does. But what it's doing here is finding some new solution to something which has value. So the documentary is really great. I would recommend having a watch of that. And the way that that AlphaGo trained was basically playing itself again and again and again, and improving and finding the ways to solve the game, to beat other versions of itself, and to improve its policy so that eventually it could beat the world champion. This is an example of a sort of simulated robot moving around, and it has learned over time here to move over obstacles, to move forward. I'm just having to change my sound here a little bit. Same for quadrupeds. And essentially what happens here is the robot doesn't know anything about physics, it doesn't know anything about movement. All it knows is when it's doing well and when it's doing badly. It has some feedback about the goodness and badness of its actions, and it uses that to do more of the things which seem to be good and to do less of the things which seem to be bad. And again, this is really the foundation of reinforcement learning. Okay, I'm going to move on from this. Some other examples. So aspects of reinforcement learning are used in self-driving cars, within manufacturing. And I actually found this paper, there was a paper on deep reinforcement learning for digital material design, where digital material design isn't quite the sort of thing, as far as I'm aware, that happens at the INRS. But it's interesting to see that reinforcement learning has been used for some types of material design. I can go into what digital material design is if you want at the end. Okay. Another example, I'll just play this relatively quickly. So this is something which is sort of one of the canonical examples of reinforcement learning, which is called a cart pole. And basically the idea is you want this little robot, which only has sort of 1 degree of freedom, it can move to the left and right. You want it to be able to learn to swing the pole to a vertical position. And what it's doing here is it's just trying random actions and finding that some of those random actions lead to the pole being vertical more of the time than other actions. And we see that at first it's completely useless at it. It just moves around randomly. But now we see, after really a very few tries, it's beginning to spend more time vertically. It's not quite got there yet, but the point here is that if we wanted to program this in by the rules of physics, by actually getting it to move in just the right way using mechanics, it would be relatively difficult. And if anything changed within the system, if the friction changed within the system, if you poked it, you'd have to program that in as well. What we're doing here is get a system to learn by trial and error, and you can see it works remarkably well. Okay, so the point about all of this is that teaching the rules as to the best thing to do in a particular circumstance tends to be relatively difficult. If you look at chess, if you wanted to program a computer to be good at chess by teaching it exactly what to do in every situation, I mean, it would be impossible. There are far more possible chess positions than there are atoms in the universe. No, that's not entirely true, but there are at least as many permutations of moves than there are atoms in the universe. But teaching every single one of those rules is clearly very difficult. And even finding sort of subsets of those rules is very difficult. So it's much easier when the system can learn the rules for itself. So the point here is that all of these have sort of the idea of trial and error in common. And you might have thought that this might be a sort of a form of supervised learning. But the point here is that the feedback that you're giving to the system is what's called evaluative. That is to say, all you're saying is, yes, this is good, or no, that's bad. Or sometimes this is very good, that's moderately good. This is very bad, that's moderately bad. Versus instructive, where instructive, you would be saying, you shouldn't have done that, you should have done this. So reinforcement learning is not using instructive feedback, it's simply using evaluative feedback. And that evaluative feedback might be the score of a game. So sometimes that's going to be a sparse reward, like in chess, where the only reward that you get is whether you've won or lost the game at the end. Or it might be something like the game of bouncing the ball off the paddle, where you see the score going up relatively frequently. Okay. So we need to formalize things a little bit more now, and this really comes back to Richard Bellman's 1957 idea of within optimal control theory and dynamic programming, sort of putting these together and introducing the idea of a Markov decision process, which is how we formalize the mathematics of all of this. So don't be too scared about this. I'll talk you through it. So here we have what's called a Markov decision process. I seem to have lost the mouse at the moment. Let's go back. No, I can't see the mouse. Okay, so what we have here in blue are states. And you can think of those states as being, for instance, a position on a chessboard, or it might be S0 is you wake up in the morning and you're in bed and you have to choose an action. You know, do I get out of bed? Do I not get out of bed? Do I go to the bathroom? Whatever it might be. And from doing each of those actions, you may end up in a different state, or you may end up in the same state. So here we have actions, which are the green circles. The square blue the blue squares there are what we call terminal states, which are essentially the end of the game, the end of whatever the process it is that you're trying to do. And it might be you end up in a terminating state, which is positive, or it might be a terminating state, which is negative. So for instance, you might open the window, walk out the window, and that's your terminating state. Or it might be that you end up with breakfast and that's your terminating state. We also have some numbers in black here. So I don't seem to be able to see my own mouse at the moment, but the numbers in black on the arrows, like the +5 and the -3, these are rewards. And this is just a sort of toy example here. These are the rewards that you get, and a reward is associated with moving from one state into another state by taking a particular action. Okay, so if we start off in state S0 and we perform action A1, there's some probability, which is probability of 0.3, that we will end up in state ST1 and we'll get a reward of 5 for doing that. There's a probability of 0.5, we'll end up in state S1 and we'll get a reward of 0 for doing that. So this really is the idea of a Markov decision process. But what we need to put on top of this is what's called a policy. So here we have a set of states, we have a set of actions, we have a set of rewards, we also have a set of transition probabilities, which says what is the probability of starting in some state S, performing action A, and ending up in some state S prime. Okay, so it's conditioned on being in a state S and performing an action A. Okay. But what we want to do is to put another layer on top of this, which is a so-called policy. And a policy is a probability, and it's the probability that if I'm in state S0, I will take action AI. Okay, so you can think of that if you're in bed in the morning, there's some probability that you'll get out of bed, there's some probability that you won't. And getting out of bed and not getting out of bed, there are the actions, the state is being in bed, and you'll have some probability, which is your policy, of doing one or the other thing. Okay, and for a Markov decision process, every action on every state where the action is possible to take has some probability. It might be a probability of 0, but there's a probability nonetheless. Okay, and that's the policy. And so what we're going to want to do throughout all of this is to find the optimum policy, find the policy which gets the highest chance of getting a large reward over time. Okay. So the question here is, given that we're in some state, what action should we choose? And of course, that depends on what it is that we're aiming to do. And so now we need to define the aim of our reinforcement learning agent. Okay, so first of all, just to give you the sort of the framework for reinforcement learning, the brain here is our agent. At time, let's say time 1, we have information fed in about the state that we're in, and we might have some information about the reward that we got for getting into that state. The policy then decides what the action is that we should take in that state. So we have some policy that we've learned over time. So let's say the state is a particular position on the chessboard. And the action is whatever the policy says is the best thing to do in that particular state in the chessboard. We perform action A, AT, and the environment changes. And the environment might be, the chessboard, or the position in the computer game, or the position of the self-driving car, the material that we're trying to design. So we move into some new state, ST+1, and the environment also gives us feedback on the reward that we get. So it says, if we're in a chess game, most of the time the reward we're going to get is 0 because nothing happens until the very end. But if it's some other computer game, it might be that you get some positive or negative reward from the environment based on what it is that you did. And that gets fed back into the system. The system now knows the new state, it knows the reward, it performs some new action. Okay. And it can do this either by taking the policy that it's already decided upon, or as we'll see, it can learn the policy using this sort of feedback loop. Okay. So we can ask the question, does the world really seem like a Markov decision process? Well, one of the important points about a Markov decision process is that it's what's called memoryless. That is to say, the only thing that matters is the state that we're in now. It doesn't matter how we got to this state. It only matters the state that we're in right now. And that doesn't seem to be the case. As we move through life, it matters, how we got to this particular point. But actually, all of that past information can be encoded in the current state. So if you include as a piece of information in the current state, the path that we took, for instance, right now I'm in a particular state, and although I have a memory of the past, that memory is encoded in a particular state of the neurons in my brain at the moment. Okay, so very often, not always, but very often, you can take something which isn't Markov and turn it into a Markov process by including some sort of memory state of what happened in the past. There's also, of course, lots of information that's hidden. So generally within a Markov decision process, the agent knows exactly what the states are. Okay, it knows the state of the world precisely. But very often that's not the case, and then we need to deal with what's called a partially observable Markov decision process. And there are ways to do that within reinforcement learning. Also, what I spoke about before, there are sort of time steps. You perform some action at time step t, and then t+1, t+2, and the states change discretely from one state to another. But of course, the world is really continuous in most domains, but we can actually deal with continuous state Markov decision processes. So none of these things are particularly a problem. Okay. Right. So now we need to get into the nitty-gritty of it. Don't worry too much about what's written on here. I know I've written a lot of words, and generally that's not a great thing to do on a slide. The really important thing here is the equation. Okay. So we can talk about the path that we take through a Markov decision process, and that path is called the trace. And what I've written here is G of tau, which says the total reward as a function of the path through our Markov decision process is the addition of the rewards that we pick up at time 0. I've no idea why I missed R1 here. This should be R0 plus R1, etc., potentially up to some horizon, the end of the task. And it's simply the addition of all of them. Okay. So we receive some reward from the environment at every time step, and the total reward is just G of tau, and it's just the addition of all the rewards. And what we're trying to do is to get our agent to perform actions that at any particular step give us the largest total reward that we can possibly receive. Okay. So in fact, I've spoken about this a moment ago. This is really the idea of Pavlov's dog, which was called psychic secretion at the time. Wonderful phrase. And the point here is that the bell is associated with food. The food is the reward, but because the bell is associated with the food, we see the bell as having value. Okay. The bell isn't associated with a reward. It doesn't have a reward in and of itself, but it has value because it links to something where there is a reward. And this is really what we're going to be interested in reinforcement learning. It's going to be saying, how do we find out the value of states, given that we can find that they lead to some reward? So for instance, in a chess game, even though you only get a +1 at the end for winning, or a -1 for losing, or a 0 for drawing, we can associate, let's say, if we know that we win a game, the state of the board just before we won is clearly a valuable state to be in. And the one just before that is valuable as well, because it led to the next one, which led to a winning state. Okay, and you can work backwards all the way to the beginning of the board. And of course, it would be strange to say that the beginning of the board, the beginning of the game, where everything is even, has value. And the point is that it only has value if we have a policy which will lead to a winning game. Okay, so we need to take into account the policy, and the value of the states is going to be associated with that particular policy. Okay. So we're going to deal with a very, very simple example of a Markov decision process here. And this is the so-called grid world example. And it's basically a very, very, very simple maze where we have some start position, and from the start position we can move to the right, we can move up. The red square with the line through it is a state that we're not allowed in. It's just a square that we have to move around, just this particular example. And then there are two terminal states. There's the green one and the red one. And the green terminal state, when you arrive at it, basically on the next time step, you get a reward of +1. And the red one, when you land on it, at the next time step, you get a reward of -1. Okay, so we're going to consider some what are called sort of exact methods for solving this sort of problem. How do we figure out how to solve this maze using ideas of optimal control theory? And later on, we're going to deal with sort of the real ideas of reinforcement learning. Optimal control theory leads up to that. Okay. First of all, however, if we just dealt with the reward simply as being the addition, if I could actually count, of R0 plus R1, et cetera, well, it's not going to be, so remember, there's only two rewards possible here. There's the good reward and there's the bad reward, and we want to get the good reward. We want to optimize to end up in that good reward state. But of course, the way we've done it at the moment, we could spend forever moving around in the maze, and then if at the very end we ended up in the green cell, well, we've still optimized our reward over time. However, we want to try and get there as quickly as possible, and so we introduce what's called a discount factor, which is a number between 0 and 1. And what it does is it discounts future rewards, which says that if we have a reward far into the future, at this moment in time, it's not going to be very important. It's not going to add very much to our G of tau, which is the total reward, or total now discounted reward. So what this is going to do is that if we want to maximize G of tau, then we're going to want to get to the high reward states as quickly as possible, because gamma to the t, as t increases, as we go further and further into the future from the particular time step that we're at the moment, it's going to make it less and less valuable to arrive in that state. Okay. So what's the thing that we actually want to tell the agent to do? So what we want to tell the agent to do is to find a policy which maximizes an expectation. Okay? And that expectation is the expectation of the future reward, okay? Discounted future rewards. Okay? And the reason that this is an expectation is because there are a couple of things which are stochastic here. Okay? So this expectation is conditioned on the policy, and the policy can be stochastic itself. It may be non-deterministic. That is to say, in a given state, if I'm in a particular state at the moment, well, sometimes I'll do one thing and sometimes I'll do another thing. So we have to take an expectation over that. But also the transitions within the Markov decision process may themselves be stochastic. So we have to take the expectation value over both the policy, which is stochastic, and the transition probabilities, which themselves may be stochastic. Okay, so we formally define the value of a state. So I'm going to have to come out of here because my mouse is hidden at the moment. Oh, yes, there's a question. Yep.
Oh, yeah. It sounds like you have to have the full Markov decision process in order to do this optimization. So you have to know all of the steps in order to get it.
Perfect.
This also, I'm just trying to clarify, are you talking about a situation where you know the full Markov decision process, or does it also apply if you only know where you are and you have to choose about where you're going to go next? You don't know.
Great. No, that's exactly the right question here. So the point here is that what we're dealing with here are what are called model-based methods. And within model-based methods, you know exactly what the Markov decision process is. You know all of the dynamics of the system. And so what we're going to start with are systems where we know exactly the dynamics and we want to solve the Markov decision process. And we can do that exactly using the sort of dynamic programming methods. What we'll come onto later are methods where we can do it purely through exploration without knowing anything about the dynamics. We will essentially be exploring the dynamics as we're exploring the system. Does that answer the question?
That clarifies things. Thank you.
Great. Okay. So yes, absolutely. In the case that we're looking at the moment, to calculate this expectation value, you absolutely need to know the transition probabilities. Oh, was there another question?
No.
Nope. Nope. Okay, great. Okay, so now we want to define very explicitly the value of being in a given state. And of course, that's going to depend on the policy. So if you have a really, really bad policy where you just stay in the same state within this maze, then the value of being in any state is just going to be 0 because you're never going to get any reward. Okay, so the value itself of being in a given state is dependent on the policy. So we can talk about the value of being in this state. So S is any of the states you want to talk about. And it's the expectation value over the discounted rewards of moving into the next state and then the next one and the next one, given the policy, given that we start at state S, okay? Which basically says, under my policy, how much discounted reward can I expect to get from this state, okay? And that's the value of being in a state. In the same way that in a chess game, a particular state of the board is valuable because we know that it leads to some good outcome. Another state may be invaluable, not invaluable, I guess, not valuable, or have some negative value because it leads to a losing position. Okay, so this is the value of any particular state condition given a policy. And what we're going to want to do in this case is to find the value of all of the states. Because once we've found the value of all of the states, then we can very simply always move to the state nearby, which has the highest value, and that will take us, because of the discounting factor, to the best possible outcome. Okay. But there seems to be a problem. And the problem here is that we just said that the value of a state was dependent on the policy. Okay? But the point is that to figure out what's the best policy, that is to say where we should move, surely we should know what the values of the states are. So it seems to be a problem, but in fact, it's not a problem. We can use something called value iteration or indeed policy iteration to iteratively move through the system to converge on the optimum policy and indeed the optimum value function. So in this case, we're just going to write down what we know is the right answer. Okay, that is to say, given that we know the optimum policy, well, we can just say that the value before we're discounting it, so this is with a discount factor of 1, that is to say not discounting at all, well, every state has value plus 1, because we know that we can move from any state into the one state where we get a reward of plus 1, and indeed we get a plus 1 here. Okay, there's a -1 state as well, but every state here has reward of plus 1. This is knowing exactly what the correct policy is, which is that if we start here, well, we can move in that direction, or we can move in this direction and get to that state. Okay. Generally, in such a system, we're not going to know this, but just to give an example, we're writing this down. Let's say we now have a discount factor of 0.9, okay? Then the value of being in the state here is 0.9, because on the next move, you're going to get a reward of 1, and it's discounted by 0.9. This is 0.9 by 0.9, because it's going to take 2 steps to get to that reward, et cetera, et cetera. So the value of being in this state here, discounted, is going to be 0.9 to the power 6. Okay. In this case, however, transitions are entirely deterministic. However, what happens if we don't have deterministic transitions? That is to say, what happens if I'm in this state and I try to move to the right, but there's only, let's say, a 0.7 probability of moving to the right. There's a 0.1 probability of moving to the left. There's a 0.1 probability of sort of moving up and then bouncing back, and a 0.1 probability, oh no, I guess and a 0.1 probability of bouncing off the bottom and ending up back here. So in this case, the transitions themselves are stochastic. Okay. So what I would have to say there is the value of being in state S22 is 0.9 times 0.7 for the probability of ending up in the state, times the value of being in that state, plus 0.1, because we might end up in that state, times the value of being in that state, 0.1 times the value of being in this state, and 0.1 times the value of being in this state. So what this is basically saying is, we know that we really want to move to the right, but we might not end up doing the thing that we want to do. So the value of being in this state takes into account now the stochastic nature of the transition probabilities. Okay. Okay. So let's see what we've got here. So given some policy, what we want to do, we really want to work out what is the value of all of the states of the system. Okay. What we'd like to do is then to compare those values with a different policy and see which of the policies is best, and then ask the question, is the policy that we have always taking us to the highest value state accessible from each point? Okay. So we're going to be able to do this in an iterative fashion. So at the moment, we've got values on the left and rewards on the right, and the rewards may come sparsely. Okay, what we'd like to be able to do is to write values in terms of values. Okay, and we can do this. I'm being slightly sloppy with the notation here. So this is all reasonable. So all I've done is taken out the t = 0 step. So we have r, we've just taken gamma to the 0 times r s0, a0, s1, which is the reward of going from state S0 to state S1, taking action A0, plus, and now I've just got t = 1 to h, okay? But the point now is that t = 1 to h, okay, is itself, I can think of this as the value of being in state, whatever the state was that I ended up in, state 1 at the next time step, okay? I'm being a little bit sloppy here because I've got the expectation out here. And in fact, what I really have here is an expectation value already. Okay, but in this case, the expectation of the expectation value, it doesn't matter too much because it'll give you a factor of 1. Okay, so what this allows us to do is to write the values of states in terms of rewards plus discounted values. Okay, and this is going to be extremely important. Okay, so now let's take this expectation value and write it out explicitly, because remember the expectation value is for 2 reasons. First of all, the policy is non-deterministic. That is to say, there's a probability of taking an action A given that you're in some state S, and also there's a transition probability of landing in state S prime given that you start in state SA and we take action A. Okay, and so we can write all of this like this. Okay, so what this gives us here is the value of being in some state based on the sum over states that you might end up in. Okay. And the Bellman optimality equation, so the Bellman equation is really one of the fundamental equations of reinforcement learning. And the Bellman optimality equation says, we want the policy, the optimal policy, which we call pi star, where we always take the action which maximizes this object here. So here we're summing over all possible actions. Now to find the optimum policy, we want to just take the action which maximizes this, okay? This is going to be really useful because we can now do something called value iteration. And again, don't be too scared of this. It's going to be relatively simple. What we're going to do is we're going to start by saying that the value of iteration 0 of all of our states under the optimum action is 0. Okay, so we just say everything is 0. Okay, we then utilize this value under iteration 0 here in the Bellman optimality equation, and this defines some new set of values, which says that now the value in iteration 1 is maximizing over A. We've got our stochastic part here. We don't need pi because we're maximizing over A, is whatever rewards we pick up plus gamma times the value of the states in the previous iteration, which in fact was 0 in that case. And now we can do the same thing again. The value under iteration 2 is equal to the same thing, but now we've got gamma times V1 star, where now this V is this V here, V1 star, where this comes from the rewards that we picked up last time, plus, well, 0 in that case. And we keep doing that, and it turns out that this converges. Okay, and then having got to some set of values which we are happy as being convergent, we can then read off the policy from this as being the set of actions which maximizes, again, the value of all states. Okay, and we'll run through an example of this now. Okay, so let's run through an example of this again in grid world. Okay, so we start off iteration 0, the value of every state is 0. Under the first iteration, the value of the states only comes from the reward. The value in the values in the previous time step were all 0. So here, all we have is the rewards and the only rewards are the +1 and the -1. So the only states that have value here are the +1 and the -1 states. Okay. Under the next time step, however, V2 star, now this state here picks up some value because it's associated with moving to this state here, which we've now said has value 1. Okay, so now this V1 star does have a non-zero value and does contribute to this state here, even though there's no reward associated with being in this state. And we can do the same thing again, iteration 3, iteration 4, iteration 5, and we see that essentially the rewards iterate backwards through the process until we converge on some set of values, and these are the converged values, under the particular Markov decision process that we defined here. So now we see that after convergence, this state has value 0.8, this has value 0.6, etc., etc. And now, having found all of these values, we can say, what's the policy? What's the best thing that we should do? And of course, from this state here, we have a choice of moving to that state, which has a value 0.34, or this state, 0.29, and we should always move to the state which has highest value. So this is the best path. And the reason that this one isn't, even though it looks sort of symmetric, is that there's the reward of -1 here. And remember, the transition probabilities are stochastic, which means that if we're in this state and we try to move up, we might accidentally move to the right. Okay, so that's the reason that actually this is the best path here. Okay. Okay. So as was asked earlier, in order to do this, we needed to know the transition probabilities. That is to say, we needed to know exactly what the Markov decision process was. We needed to know the entire model. Okay, but you don't always know that. You know, given some system, if you put a robot in some environment and ask it to do some task, you don't want to program in exactly what is the model of the entire environment. You really want the agent to be able to do things through trial and error. So I'm just checking the time. Okay. You want the agent to be able to do things through trial and error. Okay, and that's what the modern basis of reinforcement learning is about. What we did previously was we used dynamic programming to essentially use the previous information we had to update to tell us about the values of states, and then given that, we can find the optimum path through our system. But given that generally we don't know what the model of the environment is, we're going to want to sample from the environment. Okay. So there are various pros and cons of dynamic programming. It actually turns out that they're fairly efficient for a given Markov decision process if you know the model. Okay. However, very often you're going to be in some system where you might know the Markov decision process, but there are an enormous number of states. So for instance, Tetris has 10 to the 60 states. So even for a relatively complex Markov decision process, dynamic programming is going to be impractical unless you have some set of function approximations which you can use, which we're actually going to talk about a little later on. Okay. So what we can do is to use something called a Monte Carlo method. Oh, was there a question? No, I heard something. No, okay. Okay, so we're going to talk about Monte Carlo methods, but in order to do that, we're going to change our definition from a state value to what's called a state action value. Okay, so remember, a state value was basically, or the value function V of S was basically saying how valuable is it for me to be in this state S. The state action value says how valuable is it for me to be in this state S and perform action A. So it takes into account two things: the state and the action that you take. Okay. So just very quickly, so now we've got a state action value. So the optimum state action value under the optimum policy is a function of the state and the action. Now we don't have any maximizations here, and we don't have any policy in here. It's the same thing as before, and you can actually prove the Bellman optimality equation for state action values, where again, now we have our Q here rather than our V. Okay, so this is what the Bellman optimality equation for the state values looked like. We had to maximize over the A's, but here we're talking about the value of being in a given state and performing an action A. Okay. So just as an example, here for every state we would have 4 actions. So for instance, here this would be Q of being in state S1, 0 and taking the action move to the right. Okay. So how could we do this without having a model? So let's say that we start off with some policy pi, and we want to calculate Q of pi, the Q based on the policy pi of being in a particular state and a particular action. So what we could do is we could start in some state S and take some action A, And after that, just follow whatever our policy says. We can start off with some random policy. We follow along, we go through our system, following the policy pi, and along the way, we might pick up some rewards. And then when we get to the end of the game, we feed back that information to the state and action that we started in and say, okay, well, now I know something about this. Now I know that if you, under this policy, as I move along here, I'm going to sample and I'm going to pick up rewards, and I'm going to pass that information back. So now I know something about the value of that state action pair. Okay, and I repeat this, I do it over and over again, and I average the returns, because of course we've got a stochastic system here. The transition probabilities may be stochastic, the policy may be stochastic, and I do it again and again and again. I go all the way to the end of the game. I feed that information back, and now I've got some information about the value of that state. Okay. There are various problems with this, and actually one of the problems is that we have to move through the whole system, possibly a very large number of actions along the way, in order to find out information about this one state here. Okay. Of course, I can also feed back the information to the next state that I moved into and the next state that I've moved into, but I generally have to move through many transitions within the environment to get any information about what's happening potentially at the beginning. Okay. I also need to start off in every single combination of state action values in order to get that information, and that itself may be computationally expensive. Okay, we can overcome this by starting in different state action pairs, and that's fine. So a Monte Carlo method, what we're saying here is that we don't need to know the model. Okay, the environment has to have the model built within it. Okay, but what we can do is simply sample from the environment. We start off in some state action pair. We don't know anything about transitions. We just perform whatever our policy tells us. We pass the information back, and then having found the values of states using this, we can now find a better policy. Previously, we started off with some random policy. We found the values of all of the states, the values of the state action pairs based on that policy, and now we can come up with a better policy because now we have a bit more information. Now we can do the same thing again based on this new policy, which is based on a bit more information, and again, update our state action pairs, figure out a new policy based on that, and iterate this process. Okay. However, we're going to do something which is kind of simpler than this, and this is called Q-learning, and this is probably about the most fundamental of the modern reinforcement learning algorithms. Okay, so essentially, this is like Monte Carlo, the Monte Carlo method, where you move through the entire environment, but one step at a time. Okay, so what we're going to do is we're going to start with some arbitrary set of Q values. So we have our state space, and we just randomly assign every state action pair some particular Q value. Okay, we then choose some particular state S within the system, and we choose some action A from S using what's called an epsilon greedy Q. That is to say that most of the time we choose the action which gives us the highest Q value. Okay, so we're in some state S. Let's say there are 4 different actions we can choose. Most of the time we'll choose the one which has the highest value, but epsilon of the time we might choose one of the other ones randomly. We take action A, and the environment gives back to us some reward. Okay, what we're going to want to do is to update the previous Q value based on the new information that we have about that reward. Okay, so what we do is we define a target for that S prime, which is the reward that we get plus discounted Q value of being in that state. So remember, a state might have a reward associated with it, but it does have a Q value associated with it. And so we can add the two together to get our target. Okay. Based on this new information about the reward that we just found there, we want to update the previous Q value under iteration k+1, doesn't matter too much about that, but we want to update the Q value based on this new information that we have. And we're going to have some alpha, which is the learning rate. And what we want to do is we want to take the previous Q value we had, the new target, and just move ourselves a little bit more in the direction of the target. Okay. So the way to think about this is you're moving through some game, you're playing some game, you move one step ahead. You think you're in a particular state with a particular value, taking a particular action. You move to the next stage and you find surprisingly that you get some high reward in that next state. We want to feed back that information one step to update the fact that actually we should think of the previous state that we were in and the action that we took as actually being maybe a bit more valuable than we previously thought. Okay. Turns out that if we iterate over this, Generically, this will converge and we can find the optimum Q values for our system. Okay? And this is the fundamental idea of what's called a temporal difference learning method, which means we're simply bootstrapping our Q values based on new information that we have and we pass that back. So you can think of Monte Carlo methods as going through the whole game and then feeding the information back. Q learning, we just move a single step and move the information back, but doing this again and again and again, we can iterate and information from the end can propagate all the way backwards through the game. And it actually turns out that this can be a very, very efficient method. Okay. So what we're doing here, remember, is we're learning in a model-free way. We don't need to know the model of the environment. We don't need to know what the Markov decision process is. We do need to know what are the states and possible actions within the system, but generally within some game, within some system, there's going to be a set of rules as to what we can do given a particular state. Okay, but generally, so we're going to have this queue of S and A, and there may be a very large number of states, 10 to the 60 for Tetris, and there may be a moderately large number of actions that we can take. So we can think of this as a Q table. We've got states and we've got actions, and for every state action pair, we have a Q value. And so we can imagine that for Tetris, this Q table of Q values is going to be enormous. It's going to be completely unwieldy. We certainly can't do this for Tetris because we can't write down a system which has 10 to the 60 times however many actions there may be, that many Q values. We can't do it. So again, there's a lot of text on this page. I apologize for this. You don't need to read this. It's more to remind me. So what we can do is that we can think of Q as a function. In fact, Q is just a function and is a function of S and A. And it turns out that there are very good ways that we can approximate functions. Okay, we can approximate functions by fewer parameters than there are degrees of freedom in the whole system. Okay, so for instance, you could think of writing down some set of basis functions. We might have some set of basis functions f, I, where I labels the basis function of S and A. Okay, so maybe we could approximate the true Q value by some set of parameters theta, which is just theta 0 times the first basis function, theta 1 times the second basis function. You can think of this as some sort of maybe some truncated Fourier series, let's say, where now the set of parameters just the Fourier coefficients, and we add them together, and it's going to approximate our true Q function if we choose appropriately the value of the values of the parameters. But now, as long as we've done this reasonably well, we can have fewer parameters than we had number of elements in our Q table. And so long as there is structure in the Q table, and we choose our basis functions appropriately, we should be able to get a much, much smaller representation, even if it's not a perfect representation of Q using some sort of function approximation technique. Oh, yes. No, I heard something. No, okay. And for those of you who've done any sort of machine, I'm hearing something. No, okay. So for anybody who's done any sort of machine learning, you'll know that one very, very good way to approximate functions is using a neural network. In fact, we can think of a neural network as what's called a universal function approximator. At least in a particular limit, we can approximate any function to any arbitrary accuracy using a neural network. Okay. You don't need to go into the details of this, but basically what we can do is we can parameterize our Q values, and we can use this idea of updating the Q value with the target value and moving slightly in that direction to basically perform the idea of gradient descent, backpropagation by gradient descent, to update the parameters of a neural network using the difference between the Q value that we had and the target that we found. Okay. So all we do is we find the gradients of this expectation value based on the, as a function of the parameters theta, so the gradients in the different directions of the parameter space. You update the parameters, and so you can use a neural network to learn a Q value, learn all the sets of Q values, or learn an approximation at least of the Q values. Okay, so in fact, this is called a deep Q network, DQN, and this is one of the fundamental algorithms that was developed just a few years ago, whereby we can use deep neural networks to learn by trial and error within very, very complex tasks. So one of the first examples of this was actually on the Atari games. So there's a suite of Atari games. And at the time, this is actually quite a few years old now. We see here, we've got a line here where this line is the line of the sort of human level abilities within the various different games, from Pinball, Atlantis, all the way down to Gravatar down here. And we see how well DQNs were doing, and something called a double DQN, which uses another set of networks. Details don't matter. And we see that for some of the games, it was able to do far, far, far better than any human was able to do. And some of the games, it was not able to do that. Actually, now in the last few years, we've managed to come up with systems which can do all of the games to superhuman levels. In particular, one of the Google algorithms called mu0, which is sort of a what came after AlphaGo and then AlphaZero and then mu0, is able to solve all of these games to superhuman levels very, very efficiently. So it's possible to do this. At the moment, what we've been doing is finding the set of Q values, and then based on the Q values, we define the policy as the thing that moves us around the optimum Q values. It's actually possible to do this directly on the policy. So rather than trying to find out what the Q values are, the optimal Q values, you can find the optimum policy directly. And these are called what are called policy gradient methods when we use neural networks to do this. I'm not going to go into the details of this at all, but it's possible to find optimum policies directly without ever having to think in quite the same way as about the Q values. Okay. I know that I am essentially out of time here. So just to say a couple of quick points about some of the recent developments. A really nice development just a few years ago in 2018 was this idea of world models, where we spoke at the beginning about model-based reinforcement learning, where you need to know the model. And then we spoke about ideas like Q-learning and Monte Carlo methods, where you don't need to know the model. What if you are trying to simulate the model of the environment as you go along and you utilize that? Now, that's what we would very often do. You know, you perform some task and you might have some model in your head. In fact, this is really exactly how we do it. You know, all of perception is a sort of living hallucination, but you have a model in your head of the way the world works. And you might very often run through that simulation based on your experience within the world and utilize that in order to perform optimal actions. And it turns out that we can actually do that within reinforcement learning agents as well. Some things that we're kind of working on still to be figured out are ideas about transfer learning. So you can learn one task and then you can transfer that knowledge very well onto another task, so long as the tasks have some sort of similarity. This actually turns out to be very, very difficult within reinforcement learning, but it's something that's being worked on in detail at the moment. And then multi-agent reinforcement learning, where you might have multiple agents within an environment where they may be trying to cooperate or they may be trying to compete. But trying to figure out the best algorithms to get them to do this within an environment is the subject of multi-agent reinforcement learning. And it's some work that I do with an organization called InstaDeep, who are really some of the people at the forefront of this. If you want to see some really impressive reinforcement learning agents, have a look at some of the videos of OpenAI's Dota 2 agent, which was able to beat the world champions back in 2018 at a very, very complex multi-agent game. Worth a look at that. There was a nice paper by David Silver and Richard Sutton and others called Reward is Enough, where it was really asking the question, you know, all we're doing here, the only information that the agent has from the environment is about the reward. Okay? And the question is, simply having that, is that enough to perform, you know, interesting, complex tasks? And essentially, their hypothesis is that yes, you know, one is able to perform arbitrarily interesting, sort of generalizable tasks simply using the reward function. Okay, I've got a whole lot here that I can go through if people want to know more about neural networks later, but for now, I'm going to stop there. So yeah, if you have any questions, I am very happy to answer. Thank you.
Thank you, Jonathan. I think this was one of the most fun talks we had so far. So
that's great. Thank you.
Understand in a very simple language. Questions?
So I
at the beginning, you talked about secondary reinforcers, and you also specified that essentially, as it is contextual information which do not define the subject. I think that like you are looking at the cat, for instance, the picture. I was just wondering if you could say a little bit more about it, because my understanding interpretation would be that essentially those would be traps for the model, that it will look for correlation, it will find some correlation while there is no causation.
So I don't know if somebody, I caught about 2/3 of that. I think there's a little bit of echo. If somebody closer to the mic can reiterate, I'm sorry about this. Sorry, thank you.
Can you hear me well now?
That's perfect, thank you.
So my question was a little bit convoluted. So basically you were talking about secondary reinforcer.
Right.
And I was asking the link between those and causation and correlation.
Right. Yeah. So it's a this is a really it's a really interesting topic. The idea of correlation within correlation versus causation here. So indeed, the agent has no idea about causation. And the sort of hypothesis here is that you don't need to know about causation. You do need to know about the underlying correlations. A very interesting question is, what happens if you do understand about causation? Okay, if you do understand about causation, can you do more with an environment to potentially sort of make hypotheses and do counterfactual reasoning than simply understanding the correlation? So yeah, it's a really interesting question. It's not an area I think that there's been a lot of research done about it. I've actually got a master's student at the moment looking at how reinforcement learning agents can learn structural causal models. But yeah, it's a fascinating area, but indeed within this, it's not learning anything about causation at all. In fact, there's a hypothesis about the way we move through the world, that our causal reasoning is in some sense illusory. What we do is we build up sort of arguments about causation, but we don't really understand causation. We understand correlation, and we sort of see relationships which are causal as being highly correlated or correlated in particular ways. But there are various psychological ideas about the fact that we don't, as intelligent beings, actually fundamentally understand causation ourselves. That's a topic for another time. Does that answer the question?
Almost.
Okay.
Let's say the first part of the question, but the second part of the question was if those secondary reinforcer can actually be a bad thing for the model, because it will induce the model in error. It will just, because it cannot, as you said, make difference between causation and correlation. Mm-hmm. So if actually we should not filter those secondary reinforcers and keep them carefully away, so that they do not add weight in the...
Well, so essentially the secondary reinforcer you can think of as any state which leads to a valuable state. I mean, that can be a tertiary or quaternary or whatever reinforcer, but including that is the whole reason sort of policy iteration and all of these work is because a state may intrinsically have no intrinsic value, i.e. there's no reward associated with it. But if we didn't if we didn't define value as being essentially the idea of secondary reinforcement, none of this would be able to work. So all we have here is the correlation, but so long as you build in the idea of secondary reinforcements, that is to say, I know that this state is going to lead to something valuable. I don't know how, I don't know what the causative reasoning is, but through experimentation and sampling with the environment, I can see that it does. Then you can actually prove that these algorithms converge.
Okay, thank you.
Sure, thanks.
Yeah, thank you very much. I just was wondering if you can underline the difference between reinforced learning algorithms and like normal numerical regression analysis and sort of more traditional like gradient steepest descent sort of algorithms, and so just to sort of underline what is new here about the regression, reinforced learning aspects.
Sure. So really the new thing here is that the agent has a task, and it's sampling, when we're looking at something like Q-learning, temporal difference methods, it's sampling from the environment. It doesn't have anything instructive, where if one was looking at something like supervised learning is instructive. You say, here is an object, a picture, and this is the correct answer. Okay. Within reinforcement learning, it's simply trying things out and then getting the feedback as to whether it was a good thing to do or a bad thing to do. But given that it wasn't a bad thing to do, or it was a good thing to do, it isn't told any information about what the right thing to do was. Okay, so one can think that with, for instance, gradient descent. With gradient descent in a supervised learning problem, what you give it is what was the output, what was the label that you thought it was, and what was the correct label. And you use the difference between the two to move to perform your gradient descent algorithm, to move the parameters in the direction such the next time it gives you a label which is close to the true label. So we're not doing that because you never give it the true label, i.e. you're never telling it this is the right thing to do. So I think that's kind of the difference. What I should say is that we use gradient descent within this. So in particular with the DQ learning, you're using gradient descent, but what you're trying to minimize there is the difference between the targets of a state and the previously the previous Q value that you thought was there. So you're sort of bootstrapping on the Q values. So within reinforcement learning, you may also be using gradient descent. You may be using neural networks in exactly the same way that you would imagine normally. You're doing backpropagation, you're doing gradient descent. It may be stochastic, it may be batch gradient descent, all of these normal sort of things that you have within any other machine learning algorithm. The difference here is that the loss function is an evaluative rather than instructive loss function. That is to say that the only information that you're giving it is, did you pick up some reward? And therefore, was that a good thing to do or a bad thing to do? You're never telling it this was the right thing to do. Does that make sense?
Yes, thank you.
Sure. Thanks.
More questions? I saw some excitement there. Questions, guys? More questions? Okay, so I have one question, Jonathan, because we are all here material scientists, and we think about it in terms of materials. Let's say we have a reaction. Let's say we have a CO2 reduction or a CO2 conversion. There are millions of pathways that can happen in certain environment. If I have to take Emil's plasma catalysis, we are talking about thousands of different environments where that CO2 can proceed and do the reaction, but we don't know, what will happen. Basically, in general chemistry, computational chemistry, what we usually do, we do very minimalistic analysis where we calculate barriers to the reaction at different stages, and what could be the mechanism, possible mechanism, and most of the time we are not able to confirm it. There might be mechanisms that probably the CO2 conversion or reduction is happening, but we don't have a tool to analyze all the situations. Do you think reinforcement learning could be helpful in that scenario? And also, what would you need from material scientists in order to simulate that scenario?
Mm-hmm. Yeah, that's a great question. So it seems like it is an area that one could do it. Essentially, what you need to have is some idea of reward. That is to say, some idea of the thing that you are trying to optimize, okay, and maybe some end result of some chemical process. You need something that you can change. That is to say, add a bit more of this, change the temperature in this direction, change the pressure in some way. And you can think of those as a set of actions. And so long as you can perform an action, that is to say, increase the temperature by 1 degree, you can then go back and either simulate the chemical process or actually do it in real life and get information back as to whether that was the right thing to do or not. You can then use the ideas of reinforcement learning to move the conditions to the conditions where your process is running optimally. So in fact, this would be thought of as, it's all within the realms of reinforcement learning, but there's something called a banded problem. And within a banded problem, essentially the point here is that you're sort of running things once, then you're changing something, you're running it again, and you're changing something. Within a banded problem, so the banded problems are like the one-armed bandits or the two-armed bandits, where you have a couple of levers that you can pull, and depending on which lever you pull, you may win a prize or not. And over time, you can set up a system which learns, maybe the lever on the left, some of the time I get a lot of money, and some of the time I don't get anything. The lever on the right, most of the time I get a moderate amount of money. And so the system can learn over time which are the levers that it should pull in order to get the optimal results. And so in the same way with a sort of chemical process, you can say, what are the levers that I need to pull? Change this, alter the pressure, alter the chemical composition to get the final result. And over time, by doing this, you should be able to move in an optimal direction. So one thing that I should say in the same way with our work that we're doing in terms of using sort of other machine learning methods, none of this is going to magically tell you about the process itself. You will still need something that simulates it, or something that does it in real life. So in the same way that a machine learning agent only works when you have the environment. The environment may be a computer game, and that's already done. That's set up. Or it might be a real life robot moving within some environment. The machine learning agent isn't going to do anything to sort of improve the simulation necessarily, is not going to be the thing that tells you about what's happening within the chemical process. It will just allow you to optimize, given some optimization parameter that you want to improve upon. It's going to allow you to do that through reinforcement learning processes.
I see. And so in material science, one of the biggest bottleneck is always the data. We don't usually have data for supervised and supervised learning. So in this scenario, I would assume we will need a lot of information about the initial state and the final expected states, or the states that we call as reward and not reward. And we would need different scenarios or different environments that the reaction might process through. So, and that could be computed computationally or experimentally. Is that the same problem as a big data problem? Would you consider it like how much data would this need? This kind of work you need?
So it's always going to depend on the size of your parameter space and sort of the landscape of your sort of loss function. So the way to think about that, so let's say there are only two possible parameters that you can change. You can change the pressure and you can change the temperature. If you have some very simple surface within that space, where within some region there's some optimal temperature and pressure, and in other regions, it's much worse. There you've got a very, very simple parameter space, and so it may be that you can perform essentially gradient descent within that space, either using some supervised learning algorithm or using some sort of flavor of reinforcement learning. You can move very simply from one place to the optimal place. If, however, your landscape is very complex, you're going to need to do a lot more sampling to get to the optimal position. So it's going to depend entirely on sort of the number of dimensions of your system in terms of the number of parameters that you want to optimize over, and what is the landscape of your system. So until one actually understands a little bit about what that landscape is, it's impossible to say how many samples you're going to need to run.
Thank you so much. If there are no more questions, maybe Jose has some question. He will be like, "Oh, I meet him every week." So
I know, but I have a question. Jonathan, we're using the Q value. You said that every step is going back to give the feedback, right?
Yep.
But then how is advancing to the next step? Or when it's using this feedback, it's using it only for the next step, or is it starting over from the beginning?
So it depends how you run it. So it can be that you're actually taking some trace through the system, and you're updating at each time step. You move to the next state based on the optimal Q value. You pass that information back to the previous state, but then you move on to the next state, pass that back again to the previous state. So you're always moving on. Or you could just start in random states within the system. And so there are different ways of doing this. Sometimes you might want to take the full path through and sample from that as you're updating your Q values. So generally, actually, that's really what happens. Is essentially you have a sort of cache that you sample from. And the reason for that is because deep learning or neural networks have problems when iteratively each sample is correlated with the previous one. And so instead what you do is you sample randomly from your set of movements through the space. But yeah, essentially you're moving along and you're passing information back by one. There's a whole family of algorithms where Monte Carlo methods where you go all the way to the end and pass the information all the way back is one extreme. And Q learning, where you're just moving one step forward and passing the information back, is the other extreme. You could move 2 steps forward and pass the information back, or 3 and pass the information back. Or you can move a number of steps forward and in some way combine all of the information that you got and pass that back. And that's using something called an eligibility trace, which actually has a sort of perfect mimic in what happens in the brain. So there are lots and lots of different ways of doing it.
Okay, thank you.
Sure.
Let's thank our speaker once again.